Okay, in the last stage of the DC power supply circuit, we have a voltage regulator circuit. So we have the voltage regulator. So yeah, this is the complete circuit for the DC power supply. So let's we recall back what we have learned in our previous class. The first, the input will come from the wall outlet or electrical point. So electrical point is AC with a high amplitude. So it need to be stepped down or reduced. The amplitude need to be reduced. So the reduction of the amplitude is done by using the transformer. So after that, the AC will be converted into DC using a full wave rectifier. Okay, for this example, this is a bridge rectifier circuit. Okay, after the rectifier, the signal will be in form of a pulsating DC signal. So here we have the capacitor. So capacitor will act as a filter that will reduce the fluctuation or the variation of the DC voltage. Or in a very simple word is to smooth out, to make the signal become more smooth. So to smooth out the rectified DC signal. Okay, and then at the end of after that, the last stage is voltage regulation. Voltage regulation is to eliminate the remaining ripple and maintaining the output voltage to a specific value. So regulate actually mean maintain or produce the voltage at a fixed value. So typically this regulation is performed by an integrated circuit regulator. Okay, there are many different types used based on the voltage and current requirement. So the box here is written as 7805. This is one type of integrated circuit regulator. So this is IC regulator. Usually we use IC because IC have better performance and can guarantee more stable operation. Okay, but in this course, we want to see the basic application of diode in voltage regulator. So actually, instead of using the IC regulator, we can use a very simple diode to regulate the voltage. Okay, for example, let's consider the circuit. We have DC 5 volt here, and then this is connected with the resistor, and then connected in series with the diode. So diode is in forward bias. So we take a measurement of voltage at this point. So this output voltage, how much the output voltage? Yeah, how much the output voltage? So I think what you can do is you can replace this one with a practical model, which is a battery, so 0.7. So when you replace the diode with 0.7, so the V out will become this is 0.7, so the V out will equal to 0.7 volt. Okay, so the output is fixed at 0.7. Let's say if you this is 5 volt, if you replace the 5 volt with 12 volt, okay, if you replace the battery, the 5 volt battery with 12 volt, what happened to the V out? The V out still 0.7. So means that the diode can limit the voltage. The diode can limit the voltage, or diode can regulate the voltage at certain value. Okay, in this case, we using a normal diode. The value is limited at 0.7 volt. So this is what does it mean by diode can be used to regulate voltage. Okay, however, using normal diode, this is not practical because the output voltage is 0.7. So this is very small value, which is not it cannot be used for power other component. So we need to have higher voltage, higher voltage, higher voltage or higher knee voltage. So in this type of application, we use a different or a special diode called Zener diode. So we call it Zener diode. Okay, this is okay, in this video we will discuss on the basic operation of Zener diode. Okay, as you know, diode have three region. The normal diode has three region. We have the forward bias. So we have the forward bias. Okay, we have forward bias here. This is voltage. This is current. Forward bias is where the conduct current. So here is the forward bias. So we have here is V knee or equal to the barrier potential. This is the first region, and second region is the reverse bias, where the operating point where the current is zero. So this is where the current is blocked. So this is at this the reverse current. This is this is I equal to 0. Okay, and then the last region is at the breakdown. So breakdown is where you apply a very high reverse voltage. So around 100 something volt, and then at this point there will be a breakdown. Breakdown is actually associated with the device is damaged. The device cannot be used anymore. So this is breakdown. At the breakdown, current start to flow, and then with at the higher current, they will induce more heat, and then it's overheating, and then it lead to the damage of the device. So we have two region: forward, reverse, and breakdown. Okay, so regular diode is manufactured to work well in the forward region. So in regular diode, as what we discussed in our previous part, is only operate at the forward. This is normal diode, and at reverse bias. So this is on and this is off. So in two condition, on off, it operate at forward bias and reverse bias. So when using normal diode, we will try to avoid this breakdown region. But however, Zener diode is quite opposite. It's quite different with the normal diode, as it operates at the breakdown. So this is where the Zener diode operate. So this is Zener diode operate. This is on state of the Zener diode. Okay, so the breakdown region, the large current exists in the breakdown region. So large current cause heating effect, and the large power dissipation damage the diode. So this is in normal diode. So the breakdown region is happen due to the what we call it the avalanche current. So this term of avalanche current is has already been discussed in the first week, if I'm not mistaken, the first or the second week. Okay, sorry, the second week. Okay, the diode can be operated in the breakdown region by limiting the current to a value within the capability of the device. So if you want to operate the diode in the breakdown region, you need to be able to limit the current. Okay, so here the special operation of the Zener diode is, this is the diode that designed for operation in reverse breakdown region. So operate the same as regular diode in the forward bias connection. So means that if you apply forward bias to the Zener diode, so it will operate same as the normal diode. So it will the current will start to flow around 0.7 volt. Okay, but however, for Zener diode, normally we don't operate the Zener diode at the forward bias mode. Okay, for the reverse breakdown, the current will start to flow, but there are two breakdown mechanisms in the Zener diode. The first one is avalanche breakdown. So this is what we have discussed in previous week. So avalanche breakdown is due to the electron with high energy. So when we apply a reverse bias at very high voltage, there will be a high energy transferred to the electron, and then this electron with high energy capable or can generate more carrier, and more carrier will have high energy, and it will lead to multiplication of more carrier. So over the time, the the number of carrier become greater, and then it leads to very high current. So this is what we call it avalanche breakdown. So another one is the Zener breakdown. Okay, so avalanche breakdown occur in both and Zener diode at sufficient high reverse voltage. So the keyword is high reverse voltage. So the avalanche breakdowns only at high reverse voltage. But and then we have the Zener breakdown occur in Zener diode as low reverse voltage. So low reverse voltage. So this low reverse voltage is the one that we design. So this is what we decided by the manufacturer. So actually, if you refer to the introduction of this video, which I show you how the diode can be used as voltage regulator. So here the Zener diode with the low reverse voltage here will reflect how much the voltage that will be regulated. And then the breakdown voltage is set by carefully controlling the doping level manufacturer. Okay, Zener is heavily doped to reduce the breakdown voltage, and the reverse breakdown voltage remain almost constant even though the current changes drastically. Okay. Okay, so this is the IV characteristic. The difference between normal, the left side is a normal diode. This is normal diode, and then the right side is a Zener diode. Okay, this is normal, or here we call it rectifier diode. So diode that used as a rectifier is the Zener diode used as a voltage regulator. So here you can see the line at the fault bias is almost the same for both. Okay, for the reverse bias region, although the shape is same, but the difference is actually the VBR. Here is VBR, here is VZ. So in general, VZ is much lower than VBR. So the Zener voltage is lower than the breakdown voltage. Okay, so VBR is actually in several hundred volt, but the Zener can be around 12 volt, around 5 volt, around 6 volt. Okay, and then another difference is in terms of the operating region. So for the normal diode, it only operates at forward and reverse bias region. Okay, but in Zener diode, it operates at reverse breakdown region. Okay. Okay. If the voltage across the diode is between 0 and VZ, so VZ is Zener voltage. If diode is between 0 and this one, the diode is operate in reverse bias region, does not function as regulator. So here, the current is 0. So current is 0. So if you remember in for the diode in reverse bias, we replace the diode with the open circuit. So this is open circuit, so there is no current flow, there is no regulation of voltage. So in order for the diode to Zener to operate as a voltage regulator, the voltage must be at least the same value as VZ, so that diode can function as voltage regulator because it operates in reverse breakdown region. So for the Zener diode to turn on, so here this is on, this is off. So either for the Zener diode to turn on, the VR must be higher than VZ. So the magnitude of the reverse voltage must be higher than the magnitude of VZ. So it need to be in this region, in this voltage. Okay, so when we have this one, so similar to the forward bias, so we can identify the knee current and knee voltage. So IZK is the Zener knee current. So the knee is actually the point where the current start to flow rapidly. So this is at reverse bias. There's no current here, but when it's nearby the VZ, actually the VZ is the knee voltage. Nearby the VZ, the current start to decrease, or the magnitude of current start to increase rapidly. So this is the point of the knee voltage, or VZ. So the current at the knee voltage is called IZK. Okay, so the reverse current must be large enough to put it into breakdown. So we need to increase the magnitude of the current in order for the Zener to operate as a voltage regulator, or in other words, in order for the Zener diode to turn on. Turn on means that the current must have some value. If the current is almost zero, this is off, in the off state. So breakdown effect begin at the knee point. Okay. To put the Zener diode into the breakdown, IZ must be higher than IZK. So here IZ is referring to the magnitude. IZ must be higher than the IZK. If IZ is lower than IZK, the Zener acts as a regular diode, which is at off state, open circuit. Zener diode maintain nearly constant voltage across its terminal for use for value for IR ranging from IZK to IZM. Okay, IZK is the knee, the starting point where the current start to flow. IZM is Zener maximum current. This is the limit of the current that can flow across the diode. Above this current value, the Zener diode will break down. So there will be a damage, cannot be used anymore. Okay, IZK, a minimum value of IR to keep the diode is in breakdown. And then IZT is Zener test current, where at this value a nominal VZT is specified on datasheet. So here this is datasheet. Datasheet is actually the document provided by the manufacturer that lists or that show the specification of the device. So in this, usually in the datasheet of Zener diode, IZT is shown. And then IZM is the maximum current above which the diode may be damaged due to the excessive PD. PD is power consumption.